slide, there is, it's very surprising. There is 1024 transistor and this scale. If you look at the scale, that's the 1.7 millimeter in one side. So there's a millimeter square centimeter area of the transistor. But the amazing thing is the transistor is based on the nanowire. So nanowire has a diameter of less than 20 nanometers. So actually it's a silicon germanium cold shell nanowire system. Those RD are highly equipment dependent. Also, we need to put a lot of labor to fabricate it. In fact, there's a 15 photo e-beam lithography process, but also accompanying like a 15 deposition or dry etching process to complete the whole chip. That's why we call the nanowire circuit and a nanoprocessor, because that's for some sort of logic computational purpose. So that's something what I did in academic training. And then 2014, I moved to Yonsei and started to my own lab and think about what's the next for my research area. So as a early career in a professorship, you don't have much funding situation, and you have a very few students to start with. So you need to come up with the very quick the research to focus on at the very initial stage. So here's the thing: instead of very complex fabrication process, we focus on very easy process, but the performance of the device you fabricated is very comparable to the silicon technology. Okay, that's the sort of scope we focus on the first. But the thing is, you need to look at it, the different device concept. For example, for silicon technology, you use nanowire to make a circuit, and that's for active circuit element, which is the transistor. But here, what we focus at the time is we make a new device, but it's not active circuit element, but instead that's the passive circuit element, which is the capacitor in this case. Okay, so here's some of the product out of those process. One is that, so what you see in our previous slide, let me go back to previous slide first, okay. Okay, so in this slide right here, so surface is the just the paper. Okay, it's a letter paper. You just print out the every day. So there's the paper. Here's the carbon trace, which is you draw with the high quality of graphite pencil, and you deposit. So you define the electrode on a surface of the paper. So what you can do, you make a capacitor. So we make one set of carbon electrode on top of a surface of the paper, which is very rough. And then you make one another and you sandwich it. So that's the metal insulated metal structure, which is MIM capacitor. So what you can do, as you can see on the top, you can make some sort of a touch sensor out of it. And it depends on the magnitude of your touch. You can define the soft and hard. That means you can push hard, you can type the capital or small letter. So as well as the XY registration, you also define the G direction input, which is a 3D touch capability you can realize out of the very simple writing process on a paper. And the bottom video, we use the same concept, but we applied that concept onto just the paper porter, right? So which is the very transparent paper porter like this. That's the substrate. And you do some engineering on the surface to define the electrode, and you make a tool and sandwich it, and therefore you can make another touch sensor out of it. Okay, so that's the one of example. What we call this omnipresent electronics. So omnipresent means it's everywhere. So you can you see very uniqueness of the material, and you apply that material into right application. So that is the capacitor, which is the passive circuit element in this case. So we can't make activity by circuit out of a paper. That's why we call the paper electronics. You want to make a transistor out of a paper, but it seems to be very hard. I would not say it's impossible. It's pretty hard. But if you look at the other side of a circuit element, maybe it's possible. Okay. So on top of it, so what we do, we put that the touch sensor on top of the cellular phone. So what you see in the video is we program it. You can recognize where your touch is precisely seeable. But once you touch on top of the sensor, your device cannot recognize where it's touched. That's because your cell phone is operated as hundreds of megahertz electromagnetic wave. So if I say very quickly, okay, so here's the electric field. This goes out, but your sensor part right here is made of the conducting electrode. So conducting electrode, you have a lot of electrons. So your electromagnetic wave is interactive with the electron. So your EM cannot penetrate the conducting material. That's why your device cannot recognize the where it's touched. So in order to solve this issue, okay, we need to understand what's the physics behind it. That's what we call the plasma frequencies, you know. So when we talk about the transparency, respect to the electromagnetic wave in a metallic material, we need to consider the plasma frequency. For semiconductor, you need to consider the band gap. So your H mu is larger than band gap, it will be absorbed, or otherwise, your band gap smaller than H mu is going to be transparent. Right? So this is typical. So is plasma frequencies material's intrinsic properties. So every material at given temperature, your plasma frequency is fixed. That's the material's property. So below, you shining just some electromagnetic wave on certain material. That below the plasma frequency of your material, that will be blocked. So that will be reflected. And then above the plasma frequency, which is a high energy frequency, will be penetrated. Okay, that's the common physics. So here's the thing. This curve right here, that represents the normal metal. That's why your metal, the plasma frequency located right here, that above roughly 350 nanometer wavelengths. So therefore, your visible light will be reflected from the surface of a metal. This represents ITO. So the engineering perspective, in order to control the parameter of ITO, you need to lower the plasma frequency, but at the same time, you need to sacrifice the number of electrons as well. But still, that's usable as an electrode. So what we want to do, here is the typical behavior of P.PSS. That's the commercially available polymer that is very conducting. Your plasma frequency is about 10 to 11 frequency hertz. Okay. So in order to realize previous concept, you need to lower the wave low 10 to 8, which is 100 megahertz. Okay. So at the time, so that's the Maxwell equation. Based on Maxwell equation, if you give up the plasma frequency and a lower frequency zone, you need to give up the concentration, electron concentration. Okay. But for touch sensor, it's okay, which is, it's capacitive touch sensor. So here's the graph that what I want to do. Here's the commercially available P.PSS, but you need to lower the carrier concentration at that level. Is okay for a touch sensor. That's because if you look at the Garman equation of capacitance, okay, which is the your dielectric constants multiplied by your dielectric, let's say, it's kind of it doesn't come up in my mind, but it's dielectric constant and your area divided by the distance. So what the thing is, there is no is conductivity of material in that governing equation. So your conductivity of a conducting material does not matter when you build the capacitor. Okay, so as long as you can accumulate the charge at the surface of a metallic surface, it's okay. It's still usable for electrode and capacitor. Okay. Okay, so here's the scheme. We make this some sort of a capacitive sensor, which is touch sensor once again. Okay, and then confirm your electromagnetic wave, which is at the frequency of 100 megahertz. Okay, so it's a 10 to 8 order of hertz. It's very transparent, even though you used conducting material. So it's like just like an insulator. Okay. Okay. So here's the result. So here, if we touch, I use the pristine commercial P.PSS in this case. Here's a much diluted P.PSS, which is the lower concentration of the carrier, charge carrier, but still usable for capacitive sensor. Here, your cell phone does not recognize where you touch, but in this bottom case, it's possible. So if you look at the scheme right here, radio frequency 100 megahertz electromagnetic wave can penetrate this device. Okay, so we what the thing is in this scheme, we engineer transparent electrode, but it's not only transparent to visible light, but it's transparent to a radio frequency. Okay, that's the major concept in this case. Okay, once you make the dose of electrode, you can do many things. Let's say here's the pressure sensor, a capacitive sensor. And then not only you have XY registration, but also you have a G direction registration, which is you can do a 3D touch. It's a hard touch, very simple letter you can write, and a hard touch you can do thick letters. Okay, so that's the only the thickness of your devices, like OHP film, like that. Okay, so if you just go back to think about what's the previous 3D touch, the architecture in, let's say, some of the companies, the cell phone, they build inside the pressure sensor inside of cell phone, but this case, just like accessory of cell phone, it's kind of protection layer of cell phone, the screen. You put up the one layer of the OHP film of the thickness of this, but you have a 3D touch capability with that accessory. I think that's the one of the concepts you can apply. The other thing is we also use that sensor in some sort of medical purpose. So instead of we putting some human inside this MRI machine, we decided to use this orange because it sort of has a similar biological environment that has containing the water in orange, so we can is usable in MRI. So what the thing is, we put here. So here we some sort of expand this orange by putting the air tube inside. So you can put the air, and then you can expand and contract of entire the volume of orange. So we mimic a human cardiac system. Okay, so it's kind of numerically pump the orange. So the reason why is, let's imagine that you have some electronic device implanted in your cardiac system, and then you are in the situation, goes under the MRI, the test, and the question is, with those conducting electrodes containing electronic device, you can clearly image your biological organ in MRI. That's the question, right? Because MRI also, like a cell phone, is operated by the hundreds of megahertz rhythm. Okay, so here there's nothing. Of course, you can very clearly imaging the orange, but if we have very conducting material like aluminum electrode and a very pristine commercially available P.PSS electrode, there is the blocked area. You cannot image it because the radio frequencies come out of MRI device. they cannot penetrate those devices. They block, they reflect it. That's because that's all about the Maxwell equation. Your electromagnetic field is interacting with the electron. They cannot go through. So here's the one. Even though you have a device, and you can check up to here. So you're dramatically pumping the orange up and down, which means you expand the swell, the orange, and you can still has the signal right here. It's a screen right now, but also you can at the time very clearly image the some sort of, let's say, mimical biological system. Okay, so that sort of stuff we call the omnipresent electronics. So we can easily look at the what's the omnipresent material can do. It's not embed like silicon technology, but you look at the different side of technology, which is silicon cannot cover it. Okay, so let's go back to this first slide that I showed you initially. Say again, there's the 1024 transistor in there in a 1.7 square millimeter area. That's amazing. I think that's still is the world record in terms of the number of transistors we made. Okay, so if you look at I want to look at this tile right here. Okay, so if you zoom in, that tile is consist of like this. Okay, and then if I zoom in right here in this part or this part, which is the transistor, set of transistors there. Okay, so electrode, which is you see 10 gate right here, and the gate, the width in this case is 200 nanometer, which is of course I drew that with the electron beam lithography. So the 1.7 millimeter chip is combining result of a photolithography, which is you define the big electrode and a smaller one, which is say self micrometer feature you need to define with the even lithography, which is it's very time consuming, and also it's very labor and also very expensive. You need use the very expensive tool to draw define all the electrode like that. Okay, so I look at the different side of the lithography as well. So I think most of you is familiar with what the photolithography is. Typical photolithography technique. Well, even though we said that's the contact printing between the mask and a PR coated surface, but it's not true. Because think about the size of wafer. Let's say you are starting with a very small wafer, which is 4-inch wafer, let's say, and then you need to have a 4-inch mask as well, and then your mask is contact with the surface, and you expose it with under UV. And then the 4-inch wafer, which is diameter is about 10 centimeter, right? So if you look at the whole diameter is 10 centimeter, and there is always gap between the mask and photoresist the surface. There is always gap. Okay, that gap is tens of nanometer. So even though think about the roughness of your the photomask and a surface of a photoresist cover the surface, it's inevitable. There should be the gap, even though it's tens of nanometer. But the problem is, if that gap is over tens of nanometer, your UV, okay, is light source will be diffracted at the edge of metallic photomask. That's the issue. So what it means, if you are the expert, if you're a student or postdoc, go into the clinic right now, and you do the photolithography, use the typical, let's say, the Shipley 1805. That's the typical photoresist. It's a negative photoresist, and then you get, if you get a 2 micrometer feature of electrode, you are very successful. Okay, that's not because your photomask is small enough. That's because you always have a diffraction issue. Okay, so in opposed to that case, if you realize the near field, which is the UV is not diffracted at the edge of the edge pattern, you will get the absolutely nice pattern, which exactly matching with the photomask. Okay, that's the one. So in order to do that, you need to realize the zero gap between the mask and a photoresist. Zero gap, really is a zero gap between it. So how you realize it? So the thing is very simple. So we embedded chromium pattern inside the PDMS, which is elastomer, because elastomer is required because your surface is not absolutely flat, and you apply the pressure, and then using the elastomer, you can make sure all the pattern is complete contact with the surface. Okay. Okay. So the reason why I didn't make a chromium on top of PDMS is that's because your chromium pattern you deposit is already over tens of nanometer. Okay, that's because we need to embed it to make a perfect the contact between the two. Okay, so here's the this is very beautiful example. This is a substrate right now. That's the PDMS. So this is a PDMS part. So black part is PDMS. This black part is PDMS, and then blue dot is chromium. So this part is well focused, but this is not. That's because your PDMS is not rigid. It's kind of flex away, right? So that's the focus. One is out of focus. This example of your Photomask is flexible right now. Okay, so line is perfectly okay. The issue here, if you make a nanostructure which embedded into the PDMS, your PDMS can be absorbed strain that will be caused by the process of deposition. So there is no crack. That's amazing. There's no crack in even metal line. Okay, so details of a mechanistic study, we published the paper. Okay, so here's the chromium pattern on top of a PDMS. We can do, of course, this is defined by the even therapy. And then we use that mask and then put it on top of the photoresist and I expose it and then develop. That's the final develop the features. So you can realize the 61, like a 60 nanometer feature line width. But the important things, I forgot to mention that all experiments in this slide I'm going to show you is done by a 400 nanometer UV wavelengths. Okay, so 400 nanometer. So 60 nanometer is kind of 1/7 diffraction limit. So you can make the dot, which is a 60 nanometer. Okay, so because your the photomask is flexible, we can only the pattern is not only the flat surface, but we can also the pattern the curved surface. So here's the top one, okay, and then we also check can we define the side pattern like this. So look at the homogeneity of the pattern is quite amazing. And also you can define now is a 40 nanometer, about the 40 nanometer. So we use the 400 nanometer UV light source, and you can realize the 40 nanometer. That is the 1/10 diffraction limit. Okay, so we can also do not only for curved surface, you can only do like a very rough surface. So in order to make a very rough surface, we mold lip, and the surface is going to be look like this. Okay, that's the PDMS as a surface, which is the mold lip. So you see a little tiny patterns right here, and if you zoom in, and there is there is no miss any dot on this pattern. So, and then also, even though you have discontinuity, which is crack on the surface, and if you look at this slide right here, so here is the crack part, and we don't miss any dot, right? So if you scan this step, the height is a couple of micrometer in height difference. So even though there is the difference in height, you can define well the feature. You can transfer the feature of the mask onto the surface of photoresist. And also, there's no missing one dot, and even though your surface kind of leaning over the one side, you can your mask can follow that geometry and define the feature very well. Okay, so one of the advantage of a photolithography is you can make a larger scale. It is the parallel writing. It's not the serial writing, just like even lithography or scaling proof lithography. So we decided to make some plasmonic structure, which is we can encoding the color information, and depending on the size, we use the plasmons, right? So we depending on the size and depending on the distance between the two dots, you can encoding the color, and you can realize a sort of a full color structure. So we made a kind of 1 square millimeter size of the plasmonic structure. But this is it's a one-time exposure, and you deposit the silver. It's done. It's a one simple process. You don't have to do even RP on it, right? So that's the taken by just a cell phone, which means you can see this color with the naked eye. So if you go back to previous literature, they show the power of a plasma, the color, etc. They all the completely plasma structure with the e-beam sorting, so which is the 10 square micrometer scale. Okay, but this is the millimeter scale. So I think that this is the largest one ever reported. So if you zoom in each part of this, and you can do go under is 100 nanometer regime. We do various coloration. It's like we do use the silver, gold, and platinum, aluminum, and you can easily multiple images from the Photomask by repeating the process. Okay. Okay, so that's the one of we do in terms of the device fabrication, and also some in terms of omnipresent electronics stuff. And the next one, I'm going to show you some of the application of the material we synthesize, and then for energy purpose. Oh, sorry, I forgot the one slide. So we have a flexible Photomask. So therefore, we can directly pattern. Is this a soft lens? This is soft lenses, so you can buy it from the store, and we can directly pattern on top of soft lens. It's not you make some pattern and transfer onto the other surface, but this is I think it's a very nice proof of concept to directly pattern on top of curved and a very soft surface as well. Okay. So now I want to switch a topic a little bit, and then utilize some sort of the 2D structure in terms of how we use the 2D materials in energy purpose. Okay. So here's the 2D, the structure of the side view, and the secondary bonding, especially van der Waals bonding, it has the length of that bonds has the more than 5 angstrom. Okay, so 5 to less than 10 angstrom region. So what if you expand this distance? Okay, it's more than 10 nanometer. That's this case. What if you reduce the interlayer spacing less than 5 angstrom? Okay, that's the one of the concept we are focusing on right now. I'm gonna explain the one of the top one first, which is you have the large gap between the material. Okay, so this process is called the spark process, the spark reaction, which is your graphene. You start with the graphene oxide, which containing the H2O molecule between the layers. Okay, and then you approach that material into the hot object, which is you want to evaporate the water very quickly. And then the speed of evaporation of H2O is transformed from is not the liquid to the gas phase. That's very fast, and it ends up with some sort of explosion like this. Okay, so here's we fill with the liquid sodium right here. So it's the melting point of liquid sodium is 90-80 Celsius degree. It's hot, and then you contact your graphene oxide, the film, very edge, and then it's going to be exploded. So as a result of explosion, your gap will be enlarged. Okay, so here's the video. So it's very quick. And then if you take the frame of this video explosion, you can get these images. You can clearly see like a very red part. That's the fires on it. Okay. So after that, if you look at the microstructure, some morphology of that microstructure, that's the typical graphene oxide. Here's the there's many bunch of the gap which is larger than 5 angstrom length scale, and even XRD, your the plane that will index this 002 plane will be gone because it's the out of range of XRD instrumentation. Okay, so the reason why we're doing this is we want to study some sort of wetting process for battery application. Because if you, when the people think about the wetting process, there's two things. One thing is to consider. One is surface energy, of course, right? But the surface energy is a thermodynamic definition of a surface energy is the your free energy change per your area change. So you always, your object, especially for liquid, for example, they always want to reduce the surface area. That's the way you reduce the energy. So that's the surface energy. But if you look at the this partial differential equation form, your temperature and a pressure, you put that as a constant, and you change the area, and what's the free energy change? That's the surface energy. So in other words, your surface energy at given temperature and a given pressure, that's the intrinsic property. So you cannot change that surface energy. It's given. You choose the material, your surface energy is fixed. Okay. So what you can do with those material, with the graphene oxide with the larger than 5 angstrom, the gap between the layer, what you can do is you can activate the other force, which is capillary force. So you can soak up the liquid into those graphene oxide, which is not relevant to the surface energy. So in the study of, let's say, sodium, the high temperature sodium metal chloride barrier fill, we always look at what's the surface energy of the sodium or the other material at the interface. But I think that this is a very first time to consider the capillary, the effect in high temperature sodium batteries research. So this is a typical example. Let's say I put like a bismuth, the metal, which is you can enhance the wettability of liquid sodium. Therefore, you can more activate the sodium transfer, which from anode to the solid electrolyte. But the concept is you don't have to know what the details about what is the high temperature sodium metal chloride battery. But the point is how you enhance the sodium wetting on solid electrolyte. Okay, so that's the stuff. So the concept we're doing is we forget about the surface energy, but we think about the different force, which is capillary force in this case. Okay, so if we have a very proper, gap in liquid, and you can soak up the liquid up to some height, that's the capillary. But if that's small, very small, you cannot. That's the because surface energy, right? So your surface energy of the wall is higher than the liquid, therefore your liquid cannot go into the that tube. Okay. So this is the where we use the Spark Geo, okay, which is the interface larger than 5 angstrom the material. You can put it into between the interface of the sodium and electrolyte. Therefore, you can enhance the sodium wetting process. Okay, so let me show you one example. So that's the liquid sodium, and you put on the Spark Geo, and you can see your immediately your Spark Geo can absorb the liquid sodium. That's interesting because even if graphene oxide is not sodiophilic material, in order to diffuse this liquid sodium on a graphene oxide, just pristine graphene oxide, it takes a minute to spread it out That's because the difference of the covalence bond of graphene oxide and metallic bonds of the sodium. If there's two different bonding that represent the different surface energy, therefore that inhibit the widespread of liquid in a very instant time. But if you adopt the different force into that concept, you can realize very quick spreading of the liquid at the same time. Okay, so therefore, we don't have to look at the details, but the concept is by using those types of material that enhance the wettability of liquid metal, you can increase the barrier performance. That's the one of the concept. So a second case of enlarged the van der Waals gap is we utilize that concept in alumina air battery stuff. Okay, so to make a long story in short, the problem aluminum air battery is the slow oxygen reduction reaction. So how can you boost up those oxygen reduction reaction? That's the main issue in this battery stuff. But we look at a different way, which is your determining step in the kinetics is the slowest step that will determine the whole process of kinetics, right? So oxygen reduction is slow, but there might be a more slow process to prevent the very good performance out of the aluminum air. So aluminum air is a pretty amazing theoretical capacity has. They has a very good theoretical capacity, but also you utilize this electrochemistry, so there is a 3 times larger than lithium. But there is many other aspects which is good. But we look at the cathode side, which is in a cathode, we use some sort of hierarchy pore size of graphene oxide in this case. But the thing is, in this case, you need to maximize the phase boundary of liquid, okay, which is the electrolyte, also vapor, which is air, oxygen, and also solid, which is the cathode. So you need to look at these different phase at the same time, because that triple phase boundary is where your desired electrochemical reaction occurs. Okay. So the question is, not just to look at the oxygen reduction reaction, but also you need to look at the phase boundary where your solid, liquid, vapor meet at the same place. Okay, so how do you maximize those points? So the answer is pretty simple. The way you can do it, so you can maximize, okay, triple phase boundary by controlling the electrolyte. That's the key. So here's some of the simulation, and we calculate what's the proper volume of the electrolyte you can use if you use the hierarchical pore of the graphene oxide. And after that, here's an example. Here, if you look at this is AA commercial battery, and you want to write up the 18 LED light bulb here. So it's not that much bright, right? So here's the aluminum foil, okay? So aluminum foil you can get just from the kitchen, okay? And then the aluminum foil use the anode, and graphene, sparkled graphene oxide is used as the cathode. And electrolyte here, I just use the sodium chloride, water-based sodium chloride, okay? So that's the very mild electrolyte. So here's one example again. If you do, let me play that again. Okay. So here's the 4 piece of the Coke can. Okay, that's made, you can write up the light bulb pretty lightly. So all the things that we consider here is not very conventional. The challenges that's considered to be addressed, but we look at the different side of the chemistry in this case, and how we can maximize the performance of the battery. Okay, so last one is really, we think about this kind of sort of bio-inspired, the new types of energy generation concept. And then the case, what if you suppress the length below 5 angstrom length scale? It's not expand, but you to compress the distance between the layer, okay? Okay, so let's look at the human neuron structure, which is, okay, so here. So this is the cross-section of the neuron system. Here's the high concentration of sodium or cation, whatever, okay? So sodium, potassium, calcium, and here's the low concentration. Therefore, you have a chemical potential difference through those membrane. So your cation is supposed to move to the other side. Okay, so therefore, this side where you lose the cation, this side is a relatively negative charge, and you have more cation in this side, and there is a relatively now is positive charge. So therefore, you have a potential difference between the two sides. Therefore, you can have some sort of potential. That's what we call the action potential. That's the neurobiologist, they measure the action potential to track the motion of whatever is behavior of a neuron in their study. And we get a concept of this. If you transfer only cation from one side to the other side, you can generate the potential difference. Therefore, you can induce the some sort of the voltage, current, power stuff. Okay. Okay. So there is 3 requirements actually. So one is so your pore size. They should be very comparable to the size of a cation, which is the 4 to 5 angstrom. Okay. And a second, your surface of the wall should be charged negatively. That's how your cation is attractive. And also you have a chlorine ion, which is the negative charged particle, will not go in through because it will be repelled by the wall, which is also negative charge. Okay. And a third, this structure in a water environment should be very stable. Otherwise, your structure will be gone. So it's kind of one, pore size. Second, your surface charge. And a third is the structure stability should be secured in order to implement those concepts into the material. And I think that's there is similarity in those concepts in graphene oxide as well. Because if you suppress the gap to match the size with a cation, which is 4 to 5 angstrom, which is originally your graphene oxide is 4 to 5 angstrom between the layer. And also you have oxygen and also the other carboxyl negative charge, the functional group at the surface of graphene oxide. And also if we find a way to confine specific portion of graphene oxide, and you put it into the water, it will not swelling and spread out. Okay, so we need some physical confinement process to do it. So easiest one. So if you see, this is the pristine graphene oxide. If you put into the water, okay, so your gap, okay, your graphene oxide film will be expanded because you attracted the water molecule inside the pore, so it will be expanded. Okay, so the way we use just epoxy. So here's the graphene oxide, the film, and you put the epoxy between it, okay? And then this is the physically confined graphene oxide channel, and you build the high concentration reservoir of sodium chloride. Here's the low concentration of sodium chloride, and therefore your sodium cation is supposed to move in this direction. Your chlorine is not, because your chlorine size is bigger than your pore size of this graphene oxide. Also, it's a negative charge. The surface repel the chlorine ion. Okay, so from high concentration to low concentration, only sodium ion is supposed to move. Okay, this idea is work pretty well. And then if you look at the stability of that structure, okay, so even we tried it tens of hours, okay, in the water, and then your the gap between the interlayer is not changed that much. And also we confirm the smaller ions move faster. That will represented by the conductance test. Okay, so I said this charge is very important, the surface of the 2D material, in this case graphene oxide, and we control the pH and look at how your conductance is changed as well. Okay, it turns out it's a very interesting result. It turns out if we have negative charge, we also do the simulation. If we have a negative charge on a surface, okay, your dehydration process of the sodium ion, those dehydration energy barriers is going to be much lower if you have a negative surface charge on the graphene oxide. So it's very important whether you have a negative charge on a surface or not. That's because, one, you repel the anion, but also, very importantly, you need to dehydrate an ion. Otherwise, your hydrated ion size is too big. It cannot go through the pore. Okay, that's the one finding I think is very important. And look at the time scale right here. You put it into the water in a sodium chloride, and you can have OCB, so above 0.3 voltage came up and lasted 160 hours. And I think this is the first time ever this charging curve using sodium chloride ion seeping technique, and it can last like so many hours as well. Okay, so here's the one another things. Here's the you put a high concentration, low concentration, and your sodium ion flow, right? So your voltage OCB comes up. Now I dried it up. So you dry all the water out, right? So your sodium is stuck in the channel, so there's no potential supply. Everything is stopped. And then instead of pouring water into the device, you only increase the relative humidity. Okay, it's like a relative humidity like above 60%. So it's kind of water will be a nuclei and it grows between the layer. Now it starts to move sodium ion. Okay, so why is that important? Because this kind of a device you can carry in your pocket. If it's too wet, you cannot carry it. So I think that's the concept. You can kind of portable energy generation device. Maybe, I'm not sure, but hopefully. Okay, so here's the example. We connected the 16 cell. So each of this is the graphene oxide, the film. Now, here's in the half, you put it the high concentration, here low concentration of a sodium chloride, and connected in series. Okay, so that's the sort of the performance you can out of those energy generation system. As a comparison, once again, I attached the AA commercial battery, and those are the light of the intensity of light up. Okay, so we can test of course, we can use by the seawater, which is the 0.5 mole of the sodium chloride as well, and it worked okay. So I think it had potential uses in the future to separate the ion to generate the practical, I would say practical electricity. Okay, so as I mentioned, there is very important to mention there is a similarity between graphene oxide and a human neuron system to make an action potential. In the case of a neuron, for our case, is a voltage, output voltage as well. Okay, so I'm gonna stop here. Thank you so much for once again inviting this great event. I will happy to answer your question. Thank you so much.
Thank you, Prof. Shim. Thank you very much for the wonderful talk. The managing editor of SmartMath. So first, I will briefly introduce our journal, and after that, we will start the Q&A section. It's a newly launched journal by Tianjin University and Wiley. The scope is quite broad. Topics include, but not limited to organic and polymeric functional materials, shape memory alloys and polymers, 2D materials, electroactive polymers, biomimetic robotics, smart textile, electrorheological and magnetorheological fluid, AI and neuromorphic devices and systems, metamorphic biomaterials, self-healing materials, piezoelectric materials, and artificial muscles. And now we are open for submission. So welcome to publish your excellent work in SmartMath. So now we are going to start the Q&A section. I will ask the questions on behalf of the audience. So the questions are collected from the live broadcasting platforms like Bilibili, Baidu Live, YouTube, and Facebook. And the first question is about the medical care application of the first part of your talk. So is there any other kind of applications in the, like monitor or sensor the movement of blood in the vessel?
Okay, so that's the good question, and also that's the one we very it's hard thinking about it, and what's the proper application out of the technology we developed. One thing is, so actually Yonsei, we have a very good, nice, huge hospital together, so we can have a very close relationship with the medical doctors in the hospital. And we talked about the one thing is the concept. If you think about the concept I've been showing you is, it's kind of electronics, which is very cheap. So it's kind of, we use that kind of use and throw electronics, right? So if you make some very sensitive pressure sensor, and also has the thickness of the one paper thick, and then if you realize that you can use that and for a dental purpose. So I don't know how to say it in English, but if you rearrange the teeth, okay, after treatment, so doctors check your teeth arrangement is correct or not. They use a tiny piece of the paper, and I ask the patient to squash it, and they feel the degree of squashing, and that's how judge the teeth is quite well arranged. So which means there is no available and also precise pressure mapping device out of your this kind of stuff. But there is actually, but the thing is expensive. So it's not widely spread a medical device, but if you use those kind of concept, which is very cheap, you can printable out of your office printer, and let's say is very your price for making such a device. I think it's very useful, and there's some sort of a proposal. So I think the concept is, as I said, we're not aiming to fight with the silicon technology in that subject. We look at the other way, which is focused on passive circuit element, and I think there's a bunch of variety to look for the other application as well, but we haven't thinking very deep much yet. Okay.
Thank you. And the second question is, as mentioned in the slide, the highest resolution is about 50 nanometer. So what is the difficulty to improve the resolution, or what is the stepping block in this part?
Oh, yeah. So that's a good question. So first thing is, so if you have a more resolution, let's say you want to compare it to EUV, so you want to go down 10 nanometer length scale. And first thing you need is a 10 nanometer mask. 10 nanometers is a mask that has a 10 nanometer of chromium pattern, whatever. Okay, so that's the one issue. So because all the pattern you define on the mask is done by the EBM lithography first, and then you use that mask as the our portal technique. And I think that's the first. So you need pretty well defined pattern. And a second is pore resist. Okay, So that's what we call the enhancement factor. So in order to improve the resolution in a light-based technique, you need to care about the wavelengths and also distance and also enhancement factors. So these enhancement factors, they contain the quality of the photo ridges. So for example, if you want to increase the resolution, you need to decrease the height of your photo ridges. Okay, so that's the one issue. But the other drawback is if you reduce the photo ridges, you cannot deposit the thicker electrode, or to the dry etching process, your etching ratio is not good, and you cannot define the well-defined feature as well. So the thickness of photo ridges is very important. And some of the feature I showed you, like a 50 nanometer best result is done by the less than 50 nanometer of the photo ridges thick. So that's the very important to control the thickness of photo ridges. But in general, the quality of photo ridges is very important as well. Okay.
Okay, thank you. And the third question is for the last part is the ion channel power generation part. So is there any prototype or design for the application of this ion channel? Is like
there's an application for that, right? Yeah, of course. So I think you talk about the question is about the last part of the talk.
Yeah.
Right.
Yeah.
So question is, what's the application? Okay. So that's kind of some sort of, we're looking at those technology as the energy, one types of energy harvesting. So which is we use the seawater, right? So seawater for converting the chemical energy of the sodium and chlorine, whatever the other cation, anion and stuff, and we converting chemical energy into electrical energy. So that's the energy conversion process. Is the one of the issue we are looking at. The reason why we are interested in those type of technology is if you think about the clean energy concept, which is solar cell, you can think about the solar cell is very clean. And let's say your electrical vehicle use the battery, that's clean because you don't do the pure combustion, the reaction. But in fact, in order to think about how you make a silicon wafer, so you grab all the sand from the beach and then you go through all the process, which is very high temperature. You make a single crystal from holy crystal silicon. That will be done by heat treatment above 1,500 Celsius degree. And where is the temperature comes from? You need to use the fuel, right? So pure fuel, fossil fuel. So that process is very, it's not environment friendly process when you make the solar cell. After make the solar cell, converting energy from the light to the electricity, that's the clean, but it's not. I mean, the pre-step is not. So the concept we're gonna put in this technology is we minimize possible pollution that can be made out of the process when preparing the device. Okay, and then use those devices to convert the one type's energy to the other. So the final target for this is we want to look at the mass, large scale seawater energy harvesting system, use the only membrane. That's the one of things that we're looking at right now. Yeah.
Okay, thank you. And our last question is about the young scientist. Is there any suggestion for the students or young scientists about their career or research work?
Oh, so okay. So I think I'm not in that position to give advice to young scientists yet. Maybe 10 to 20 years later. But I think one thing is if you decided to be a scientist or an engineer, I think you need to devote a huge amount of effort on it. I think that's the one dedication big dedication is very important. So, well, it's kind of depends on how you look the beauty of life is. But if you want to do the real science and a good engineering, whatever it is, I think you need to keep up little portion of your life, and you put those effort into the science. So I would say the dedication is the very, very important, the perspective. Yeah. But more details, I'm not in that position to give good advice yet. But thank you for asking.
Thank you. So please let's thank Prof. Shim for the wonderful talk again. So thank you so much, and see you next time. If you have a suitable paper or manuscript, then maybe you can consider to submit to SmartMath. Again, thank you.
Thank you very much.
Thank you.
Thank you.
Yeah, thank you.
Thank you.
Good night. Okay, take care. Yeah.
Bye.
Bye-bye.
Thank you.
Yeah.